It's not my fault. It's ChatGPT's, of course. So the idea is how can we improve on multi-messenger astrophysics? What do we actually need to get or make sense of this messy multi-messenger transient sky? Of course, we need efficient and rapid detections. We've heard that in various talks. Also include correlations. Also, we need to realize that there are multiple detections at the same time. Therefore, we need to share information and data in real time. We use this information then to schedule hopefully efficient and rapid follow-up observations. Again, the outcome of this observation should be shared rapidly as well. And then, of course, we need to interpret the data. First step in real time to guide further observations, and then at longer time scale in joint multi-messenger, multi-wavelength analysis. All of this requires a few basic principles you're all aware of. We already mentioned in one of the discussion sessions the adoption of open data principles. So people need to share their data so that others can use them, and therefore for increase the efficiency of their follow-up observations. So don't waste time on a source that is already ruled out, for example. And the thing that I'll focus on in this talk is the integration and interconnections of the various tools that we use throughout this process in various observatories, in various wavelengths, in various messengers, etc. So I run you through an idealized view of a hypothetical detection of any multi-messenger, multi-wavelengths phenomena. I focus on time domain studies, but this is also part of that is relevant also for archival studies, where you can combine data that you already have on disk. So the first thing is, of course, the detection. So you have the various phenomena. These send us various messengers. We try to figure out throughout the week which combination is most useful. And then you have all these large field of view monitoring instruments, monitoring the sky 24/7 to detect these messengers and therefore point back to these phenomena. Since we first created this flowchart, this figure, a few of them are gone. Gaia and Integral have been switched off, but there are new kits on the block, like the Einstein probe that came along. So this is of course an ever-changing picture. The point here is that you have these typically large field of view instruments that detect new phenomena. So they have the monitoring capabilities, but typically they do that with relatively low sensitivity resolution, be it on sky position, energy, resolution, etc. So then the whole idea is to use this information and to trigger typically smaller field of view, more specialized instruments to really study the phenomena. These detections, of course, require a real-time data analysis within these instruments and alert publication. Again, open data requirements in real time. There's, of course, a long list of examples. We've heard about most of them throughout the week. There's, of course, the gravitational wave public alerts, including the possibility to get early warnings, which is very interesting. We heard about the IceCube public alerts, GRB alerts, X-ray transients. There are real-time alerts on fast radio bursts produced by Chime. And of course, we have the upcoming flood of alerts from Ruby and LSST. And we'll continue to hear about these. So these are then published by the observatories, and they are made available to the community through a variety of infrastructures and brokers. So distribution channels, there are historic ones like the GCN that we, I guess, all know of, the transient name server. But there's an increasing number of these distribution channels that we try to monitor. There's also a kind of a paradigm shift in what these distribution channels or brokers do. Previously, basically, they just passed on information from observatories, from instruments. So if CTF or another optical survey classified an optical transient as a supernova, they sent it to TNS, and TNS flagged this event as a supernova and passed on the information. In the Rubin era, these brokers have a more central role and also play a part in the classification of the event itself. So the incoming data from the telescope is just pushed to the brokers, and they then try to figure out what the classification and characterization is. This, of course, also plays a role because we have multiple of these brokers. So the same data stream can be characterized and classified differently by different brokers. So this even multiplies more the variety of information that we get. And this is also one of the aims, to reduce this multiplication and confusion maybe of the same data being classified differently by different brokers within the ACME project, called the European Broker Initiative. Technically, so how is this information then distributed? There are various protocols, various technical implementations. One a VU event transport protocol that's being phased out. Kafka is playing an increasing role, but there are also not so useful means of distribution of information, like just putting information on a website where people then have to scrape it off. People still send emails. For example, the transient name server announces their new events by email. And these distribution means use also different data schema and serialization, so that the actual data that you look at or that's being transmitted to you comes in different formats. Again, there's a VU event definition. GCN is currently coming up with its own. Then you have serializations, XML files, JSON, Avro, whatever. So there's an ever-changing infrastructure or landscape that we have to deal with. And then typically, so in the first scenario, this information is transmitted in real time, ingested by the follow-up observatories in real time, fully automatically. So they pass through this incoming information and react fully automatically. This, of course, requires a bit of preparation. So you have to prepare for proposals. You have to have actual time on these various telescopes to be used. And then you have to filter this incoming stream of information to match your criteria that you outlined in your proposal or that you're interested in. By implementing these automatic filters and predefined source classes, phenomena that you're interested in, you should always keep in mind that this is as often or typically a limitation, because you'll only follow up events that you already know, because you could define them in your proposal. You can actually define filters for them in your automatic reaction systems. So you probably lose track of new phenomena and new surprises. And then you have the triggering follow-up observation, which is then typically deeply integrated with the actual control software of your observatory, follows various security checks, etc., etc. I don't go into these flow charts. It's just to illustrate that these are complex systems that have been put in place in most of the major observatories. This one is from the Hess high energy gamma ray observatory that I'm involved in as well. And then, so these are current instruments, but there's of course also looking ahead, a whole suite of of new possibilities coming up, always with a relatively small field of view. So dedicated observatories, they need them to tell where to point. And then they provide, again, as I said, high sensitivity and high resolution. And these provide then typically a much finer, a much refined localization and classification of the detected event. This is typically also using spectroscopy. We heard about polarimetry a bit. So this is then really the core of the science, where you can learn about the phenomena, where you can trigger extensive follow-up in time if it's worthwhile, or just classify potential candidates and then stop the follow-up because you realize they're not interesting anymore. And there the difficulty is, of course, that there's a strong competition for time at these major facilities. And this is one of the bottlenecks, as also has been outlined by Susanna earlier in the week, to actually classify the wealth of detections that we get and the increasing number of detections that we get. And therefore the fraction of the non-classified events, so that just somebody detected a transient, but there's no further follow-up, so we will never know what was going on there, is actually increasing. And of course, it will be increasing significantly with Rubin LSST. The other way, so not the automatic, fully prepared, very immediate follow-up is, of course, still manual observations, where we, of course, still also have to go through this proposal preparation phase. But then we can have the humans in the loop and use additional tools and have slightly relaxed timeframes. And there, of course, again, the main aim is to find interesting targets. So it's not, we don't have enough targets. I mean, we don't have enough binary neutron star mergers. So there are certainly source classes where we don't have enough targets, but typically you need to filter through this wealth of incoming information to find the targets that you are interested in. And this information, again, is scattered across these multiple platforms that I mentioned earlier on. Distributed also across these various means of communication, so that makes your life a bit harder to keep track of what's going on. Of course, I have to mention our own homemade solution to this issue, the Astro platform, where we try to summarize all these screens in an easy-to-use human interface. Nowadays, humans rely heavily on smartphones, so we have a smartphone app that allows you to do all of that. And again, it's not only the incoming information that is scattered across multiple platforms, it's also the additional context and archival information that is scattered across an increasing number of platforms. And we try to link to all of them, so you have this central point where you get all the transients, and then you can learn everything about them through outgoing links. So this is this multi-wavelength and archival information. We also pull in information where we think it's useful. For example, we compile light curves from a bunch of observatories, so we combine information in a single place, so you don't have to look through 3 or 4 different archives and then have scattered information again. We pull in the information directly from Swift, for example, for the GRB afterglows detected by XRT, the Fermi light curves, etc. And then we again point out to additional platforms. We have heard about gravitational waves quite a lot for the GRACE DB, the detailed information provided by LIGO Virgo in real time, and also relatively new things like Phil's XRT living catalog. And then, of course, once you have all the information, or most of the information in a central place, you can use this to discuss with your colleagues in the same project, in your same collaboration. You can share events, so you know exactly what events you're talking about, even before it's given a name by the transient name server or GCN, and then we have a discussion forum, and you find all that information on the central web page there. Again, this is an interface meant for humans in the loop, for manual triggering follow-up observations. Therefore, we have a few tools for observation planning. So you can select your favorite observatory, and you see the visibility of each of these sources for the next night, which you then can use directly to schedule follow-up observations. You can do this also across multiple observatories. So if you have time on various facilities, or you want to see which facility would be most optimal at which point in time, you can do these multiple observations, multiple observatory plans. And again, coming back to gravitational waves, we have these huge uncertainty regions. We need to derive an optimized follow-up schedule plan, and we have a dedicated platform called TilePy for that, which we are running also, which is integrated, so you can derive these tiling patterns for your favorite observatory directly from AstroCodebris, or also via an API, so you can integrate it into your own systems. And this is also part of ACME, by the way. Moving on, so you have found possibly in AstroCodebris, possibly somewhere else, your favorite transient. You want to trigger follow-up observations, so you need to send this information to the telescope again. And there are various platforms that are able to do that. One is the TOM toolkit. The other one is SkyPortal, which is also part of ACME, and that Sarah will talk about just afterwards. And these are then, again, multi-purpose platforms where you get the information and you actually deal with the connection to the telescope, get the data back, and then submit it back into the system through these. The TOM toolkit is now also being extended to the EON platform, which is dealing with multiple observatories running these TOM toolkits. So it's again one level above, trying to integrate multiple observatories and make life easier to coordinate and facilitate all these processes. I just want also to highlight one of the other platforms that is very relevant for gravitational wave follow-up. That's the treasure map, where people can actually submit planned and conducted observations to help with this coordination across multiple instruments, also different collaborations. So if everybody contributes to this, you get hopefully as close in real time as possible an overview of which region of the sky is being covered or has already been covered by multiple observatories. So this is one example for very well localized neutron star black hole merger in 2019. And in 24 hours, so this is the first day, you get the submissions of all these pointings from various observatories, of course, large field of view instrument and pointed instruments. But you also see, if you look closely, that there are little regions in the sky that have not been covered at all, while still everybody focuses, of course, on the most probable locations and probable galaxies and things like that. So there's still, this is only a tool where you see what people have been doing. It's for the moment less used to actually optimize and increase the efficiency of the coverage. But hopefully this is a next step. And then if you wait a few days more, you get then the full coverage by all the instruments who submitted their observations to this platform. There's certainly a whole bunch of observatories who did not. And this is also one additional point in time. So if you want to coordinate or increase the efficiency of follow-up observations, you need to know who is doing what. So gravitational waves, there's one attempt. There are various other attempts. So for example, there's an IVOA service called OPSLOC, where you get access to the schedule, for example, and the visibility of major satellites. And we'll hear about, so this is a platform called TOBE that is part of the Integral Science Center, and we hope that it's still around for a bit longer. even after the end of operations of integral. But there are other services like the across that we'll hear later on, focusing on NASA missions, which provide, or hopefully soon, similar services. And of course, individual observatories also publish their schedule in real time. So again, coming back to HES, we publish our GRB follow-up schedule on a public website, so people can see when we trigger observations on a given GRB and then coordinate their observations to fall close in time to get simultaneous observations, if this is interesting. Then once you have the follow-up observations, of course, you need to analyze the data as fast as possible. So there's again, the real-time analysis efforts are increasing. This is an example from CTAO, where you get these 30-second latency. So I don't go into all this detail of the flowchart, but the important number to remember is 30 seconds. So 30 seconds after the data or the high energy gamma rays fall into the telescope, you get a first estimate of what you're actually seeing. And the idea is to then, of course, accumulate data for a certain while, depending on the flux level that you're actually detecting, but then push that out to the public in some form of alerts. Again, the aim is to rapidly publish the results of these follow-up observations, which helps to guide further observations or stop ongoing observations because somebody else tells you that it's not interesting anymore. One effort there is also that you have to have comparable results, so normalized analysis methods, various instruments going through the same image analysis pipeline, for example. One of the platforms that we'll hear about in a second, again, part of ACME is Black Hole Tom, which is aiming to exactly do that. And then you have the data, and you want to do a high-level science analysis. Now you have a bit more time, but you still need to derive this complete picture of the phenomena that you've been studying. There, again, of course, we aim to be as fast as possible, but the requirements are less. There's still one issue that you need to know who actually observed the same event and whom could you contact to join forces and join a publication. So there were already at various points in time the idea to have somewhere a global information database of available data sets that does typically not include the results of the data sets or the final products, but just that you know who did observe which event, at what wavelengths, at what time range, and then you can contact the people and say, is it interesting to join forces and put these data sets together. But again, this is, as far as I know, not existing and not really pushed anymore. And then, of course, you need tools and platforms and software to actually do these joint analysis, joint global fits across all the different wavelengths, including different messengers. In the high energy domain where I come from, there's the gamma pi package, which is starting from the highest energy gamma rays, but is now being extended to include neutrino data, to include X-ray data, so you can actually analyze these various observations at a very event-by-event deep level and do joint fits and things like that. And certainly there's a huge range of other tools and products available as well. And then, of course, once the data is published, you have to try to feed that back into this system of archives, make it available and easily available. So there are various efforts nowadays to also associate your data sets with computing resources and scripts and tools. One of the efforts is MMODA, part of one of the ACME work packages, that they can actually reproduce the published analysis and change it a bit and get your own own results. Again, then the archives and catalogs and things like that need common interfaces to allow for integration into this whole landscape, so that actually we can use them in real time to guide observations and learn about previous detections of the same region of the sky, of the same source or the same source class, and therefore help again in this whole decision-making process. And that's the naive and simplified view of time domain multi-messenger astrophysics. I guess you all know that these are challenges observations, challenging data analyses, but we have actually an enormous and increasingly sophisticated set of tools at our disposal. So the main aim is now I think to further automatize and integrate and interface all of these tools, platforms, infrastructures. ACME is trying to help with that, but there are of course a huge range of open questions that are coming up, and I guess we'll come back to that also in the discussion session later on. So one thing is how sustainable is the current landscape? So we have all these platforms and tools, but as we all know, many of them are being developed by a small group of people. Then based on some project funding, after 3 or 4 years, that funding goes away, and the PhD students and postdocs move away to something else, so the platform dies. There are certainly a few single point failures in all of these platforms and procedures and flowcharts that I showed that are quite worrisome. Again, another big question that we can ask is what role AI does or will play in this aim. So I mentioned that the distribution of information is already now quite or still now based on human written texts, so small pieces of verbal text, and we have actually or we are working on AI systems analyzing this text, extracting structured information to make it useful in an automatic way. But the next step is, of course, that then also what role will AI play in the decision-making process? Which events are interesting? Which events to follow? I mean, typically we are already doing this. I mean, if the brokers, most of the brokers for Rubin, for example, use AI or machine learning tools to classify events, then if you rely on this classification to trigger follow-up observations, then you rely on AI. But of course, this is I think only going to increase in the future, and people have been proposing agents that ingest all that information that I showed and take your decisions for you on which events to follow up. And there's a whole other discussion about how we can increase the efficiency and the information provided by amateur astronomers or citizen scientists in all of that to increase the rate of, for example, classifications of typical optical transients, for example. And there's a bunch more. So just to trigger discussions. Thanks a lot.
Thank you very much for the talk. We'll now take questions from the audience.
Thanks a lot. I have a question about something that you said that is now maybe not so push anymore and so on. That is the fact of being able to have a portal where to just write in the name of a transient, find out which data are available, even privately, but I mean that which observation have been done on this transient, because I still think that this is something that it's needed and that we maybe can push within ACME and try to develop this. So I wanted to know if you think this is possible, and also if you know if something like that is planned in the view of LSST.
I don't know about LSST. Again, this has come up a couple of times in various workshops, for example, in the within Astro Colibri, we run yearly workshops and have a brainstorming session and hackathon where people come up with new ideas, what would be needed to improve all the flow charts. And this was one of the ideas, but hasn't been implemented so far. We can certainly revive that idea, and I totally agree that that would be very helpful to have. Not quite sure if ACME is the right place, because ACME is not really meant to do new developments, but only to provide services around existing platforms. But we can certainly brainstorm how to best do that.
So in a sense, it is because this is part of facilitating the access to data, in a sense that the thing that I think is a portal where you enter the name, and in fact the portal just ping different archives and see if there are values inside. So this is the idea. Anyway,
but
we can.
Then the question is, do these archives exist? Right? I mean, if you talk about transients,
yeah,
there is no archive than the GCN circulars
no, I was
about
thinking,
who observed a GRB last.
No, I was thinking more of archive of big instruments or small instruments that have archive available, like you can do it with the ISO, with XMM, with Chandra, HST, JWST, or other smaller telescope that have open archives.
And
like
this
that.
is part of ACME. I totally agree.
Yeah, so thank you for the talk. Actually, it's a bit related. In which sense the CDS structure, like CDS, can play a role in this structure? For example, for the archive, it seems to be quite obvious they can play a role, but I don't know in terms of alerts if they can, if they already think about that, or if they can play a role because they have permanent people that can work on this. So I don't know. It's
would be very
question.
Good if they could play a role, but for the moment they don't really.
They don't. So they've been contacted.
So they're more focused on archives and catalogs and.
But they've been contacted, or and they don't have the manpower, or they.
I mean, we haven't talked to them about these ideas specifically, but I mean they're aware that time domain and real time and things are getting more and more important, but I don't actually see a lot of activity there.
Thank you, Fabian. Excellent as always. I sort of following on these and something you said in there, joined together. This one of the things that I think is a potential solution to this, and is really interesting, and I'm a bit embarrassed that I hadn't thought of it until recently, is this you have with Moda, the idea that you have a data set or the tools that are used to create the data set, which are encapsulated in something like a DOI. So to come up with some kind of formalized way of doing this that everybody adheres to, that's in some beautiful agreed open standard, is going to take a millennium. But on the other hand, you know, to me, I mean, like, for example, I have systems where I know how this data set was generated. It wouldn't take too much work to be able to create a link for that. On the other hand, I have no way that I know of generating a DOI for that. And I wonder if maybe within, I don't know, Astro Colibri or some ACME package or something, a way in which you could, anyone who creates a data set could go to there and say, here is my URL and a little bit of metadata, you know, my name, my contact details, the instrument, whatever, the GCN that links to it. And you would generate a DOI or some form of static notifier that would then work as like just almost like therefore a broker that would really lower the bar for everyone to be able to provide this. Is that something you think, for example, Astro Colibri or something in ACME could do? Because I think that would address Susanna's point as well, because we just have to create an entry on there and bang, job done.
I mean, we have to think about it. I have no idea how to create an DOI, but
okay, right. No, me neither.
I can figure it out.
Oh, there's a thing. Apparently, it exists. Natalie says so. Okay.
Very good.
I know, like our university can create DOIs, but I don't know how it's magic. You ask somebody and you wait a while and something happens. I mean, that's.
Are there any more questions from the audience? In which case, I'm going to take advantage of the microphone and ask one myself. I was interested in what you said at the end about archives for projects which may be coming to the end of their funding or coming towards the end of their lifetimes. I was interested, how important do you feel it is that there is some kind of ongoing program to keep those archives maintained and up to date so that they are compatible with new observations, new observatories, and maybe the new alert brokers as well?
I mean, that's crucial, and that's certainly, I mean, you mentioned the archives, that's certainly something that is at this very moment missing, right? Because all the information flowing through these distribution means and brokers, not all of them keep track of what's going through, right? So for example, GCN is currently not keeping track of the notices that are going through. You can go back and see what has been submitted 2 months ago. We didn't set out to do that, but as we are listening to these things and filling databases, we are now with AstroCode building up such a database. But again, there are few single point failures if project funding, I don't know, GCN is NASA. Who knows what's going to happen next week? There certainly, that's what I mentioned, that there's a worry that a few of the crucial systems, which are central to all of that, don't have a fallback or backup solution. And then if they go away, as you said, the whole archive goes away. I mean, one of the examples I know was the 4Pi Sky project, which launched one of these distribution means, which put a lot of effort. One was an ERC-funded project at Oxford, which produced a lot of the infrastructure, like the Comet broker used to listening to notices, etc., etc. They had an archive. Then the project ran out. They kept the server running for another year or two, and then they switched it off, and it's just gone.
I've got about 1,000 comments, sorry. Okay, so the answer to Phil's question first is Xanadu. So you can go to Xanadu and you can register your data set, you can register even your software or some kind of thing that you have created. You can provide as much information as you want and they'll give you a DOI. Okay, so that's the first question. Second question. So with regards to this idea about upkeeping data sets, I agree it's extremely important. It's a very difficult thing to deal with. However, I don't know if you're aware. So ESA, if it needs to be something related to an ESA mission, but ESA are now very invested in this effort. So if you have a data set, if you've got a project, even if it was like something like I don't know, an 8-2020 project, or even just a big national project or something where you've developed either software, data sets, or something that makes use of any ESA satellite, ESA observatory data, they will actually upkeep that archive or that software or whatever for you and make it available. So if you'd like to take advantage of that, then you should contact the ESA Astronomy Archives user group. I am the president, so you might just even want to send me an email if you wish to, and we can take that data set on, and we can even do stuff to improve your data set and also to maybe even integrate it into ESA Sky or other things like that. So your data then will be preserved. So I think that's an important point to remember. They have thought about maybe extending it a bit further outside of ESA observatory. So yeah, it might be in the future, might be useful for everybody, but I'm sure it counts for a lot of different things anyway. I have a million comments, but I think I'll probably just keep them for the discussion center session.
Okay. Everyone, thank you very much to our speaker again.
Thank you.
And our next